Just only the second half. Does, I'm okay. All time.
Happy Tuesday. We look at triple integrals now. This is exciting. Triple integrals are also going to be evaluated as an iterated integral. So let's look at a triple iterated. So the idea is the same as with double. Bless you. You just work your way from the in out. And then the order tells you the order in which you're going to integrate. So for this one's dz first, then dy, and then dx. Fubini's theorem also applies for triple, saying that the order doesn't matter. You just have to obviously redescribe your domain. So with respect to z, xy treated as a constant, that can be factored out. And then the antiderivative of z with respect to z is a half z squared. That's going to be evaluated from 0 to 2 minus x. That's what we're going to be left with. Now with respect to y, that x times 2 minus x quantity squared is a constant. So it can be factored out. Now you're going to be left with a half y squared, evaluated from 0 to 1 minus x. Bless you. Oh, bummer. We're gonna have to expand that out. You know what? I don't really feel like doing that by hand. So I'm gonna use the CAS to expand it for me because I'm lazy. X to the fifth minus 6x to the fourth plus 13x cubed minus 12x squared plus 4x. Guess I could be really lazy. Maybe make that a little bit larger. Which I don't think I can do from here. I have to exit full screen. That'll be 2x squared from 0 to 1 minus 4x cubed from 0 to 1 plus 13 over 4x to the fourth from 0 to 1. 6/5 x to the fifth from 0 to 1. And then 1/6 x to the sixth from 0 to 1. Common denominator. Be 60. Ten minus 72 negative 62 plus, oh God, 13 times 15. Write down the negative 72 so I don't forget it. 10 times 10 is 100. 3 times 5 is 15, so there's 115. Then it's what? 50 and 30 is 80. So 195. $195 minus 72. 123. No. Yes. But then it's minus 120, which is 3, which is not what I have. So we said that's what, 10. 5 times 12 is 60, so it's going to be 6 times 12. That is 70. So that's why it was minus 62. Oh dear. Okay. So I have to add 10 to what I had. Right, so that's negative 62. I said that was what, 195? So that is 195 minus 62 would be 133. Yes, then minus the 120, which is 113. Or 13 rather. So 13 over 240. Arithmetic is hard. Now there is another property of iterated integrals that I didn't mention last time. All the bounds are constants, right? And we have strictly a product. We can also write this way. So we can just write this as the product of 3 single integrals. Keep in mind, this only works if your limits of integration are all constants. Right? So in other words, your domain is a box and it's a product of functions. The negative cosine from 0 to pi over 2, which is negative negative 1, right? So that's just 1. R cubed over 3 from 0 to 1 is a third. Z squared over 2 from 0 to 2 is 2. That integral's 2/3. Do we have a theta in the integrand? Are any of the limits of integration dependent on theta? No, right? This comes from being able to write it as a product. So it'd be the integral from 0 to pi of d theta times then the remaining double integral. Well, that integral is just pi, so there's your pi. Oh, look, there's no rho in the integrand either. That makes that integral easy. Oh, not secant phi, pi over 4. Huh. Well, how are we going to do this integral?
Not sure how you do it, but can you turn the sine to theta into cosine somehow so that it cancels out this teacher?
Theta? Well, the sine itself isn't going to become just cosine. There is an identity you can use. What's the identity? Oh, that's for squared. That's the reduction identity.
Be sine squared phi times cosine squared phi.
Not squareds. Not that I'm familiar with.
Sine phi times cosine phi.
Double angle identity for sine. Sine of 2x is 2 times cosine times sine. Oh, look at that. Secant times cosine is 1. The negative cosine from 0 to pi over 4. pi times 2 minus root 2. Cosine of pi over 4. Well, technically negative cosine of pi over 4. Bless you. Questions on the triple iterated? Fairly straightforward, right? It's just an extension of double. You just have to do one more step. However, I am not nice enough to give you iterated integrals on a test. We're going to compute the integral of z over the region in the first octant bounded by the planes y equals 0, z equals 0, x plus y equals 2, 2y plus x equals 6, and the cylinder y squared plus z squared is equal to 4. Conventionally, they represent three-dimensional domains with a W, a script W. Now, trying to describe a two-dimensional region without the aid of technology is doable. It's really not that bad. Trying to describe a three-dimensional region without the aid of technology. It's a bit of a beast. Thankfully, we have Mathematica. Let's go ahead and plot all of the relations that we were given. We were given y equals 0, z equals 0, x plus y equals 2, 2y plus x equals 6. What's going on? Why'd you go down there? And then y squared plus z squared is equal to 4. We are also told we're in the first octant. Remember, that means that x, y, and z are all greater than or equal to 0. How far out do I want to go? 5? Also, remember this is going to give us something that's boxed, so turn off the box. Set the origin 0, 0, 0. Something I always forget to do. Turn off the mesh. Just because I don't like the mesh, it makes it look too distracting. Gonna want labels. And I am gonna want legends as well. And then there's one more thing I want to do, set the opacity. Contour style, opacity 0.5. Now I just need to try and find the region that we're looking for. It is going to be this region in here. All right, so I guess for lack of a better term, that hallway. We are going to have to decide how we want to describe this region. Right, we need to choose an order of integration. There's 6 possible orders. Let's see. That's actually a pretty good look right there. Oh, you're playing this game again. Okay. Perfect. Here's the question. Does save it. Perfect. Our domain is a set of ordered triples, X, Y, Z. We now need rules for X, Y, and Z. The easiest way to describe this let y go from 0 to 2. So that's going to be our outermost integral. Now we need to choose the order for the remaining two. Do we want to write x as a function of z and y? Or do we want to write z as a function of x and y? Well, if you actually look, it doesn't matter. Both are going to be written strictly as functions of y. Right? Z does not depend on x does not depend on z. So the order in which you choose here now does not matter. So start with x next. What are the bounds for x? So you went the wrong way. You did z. Right? So remember the z-axis. The x-axis is going that way. Yes, go ahead. Change your mind, John?
Yeah.
Isn't x going to go from that green plane to the red plane? So x would go from 2 minus y to 6 minus 2y. And then z was already said goes from 0 to root 4 minus y squared. Right, it goes from the floor up to the cylinder. There you go. There's your description of the domain. Now imagine trying to do that without a graph. It's difficult enough with the graph. So when we do triple integrals, we have a volume differential. I don't remember when I looked at. I did not. Perfect. So recall that we already saw that if you just integrate over an interval I with respect to the length differential, it's just the length of the interval. Right, integrate over an integral, integrate over an interval of f with respect to the length differential, right? So x, y, z, whatever your variable happens to be. It's a signed area. And between the positive axis and the curve. Double integrals became an area differential. If you just integrate over some domain D, gives you the area of the region. Right, and then integrating a function over a domain would give you a signed volume between the plane, typically the XY plane, and the curve. Now we're in triple. The differential is now a volume differential. So what do we think this integral would give us? The triple integral, so if you integrate over a three-dimensional region, it just gives you the volume. What if you integrate a function over a three-dimensional region? Hyper what? Just hypervolume? This gives you a signed hypervolume. We just call the four-dimensional equivalent of volume hypervolume. There's no way we can even begin to imagine what that is. There also happens to be a hypersurface area. Right, which is again the four-dimensional equivalent of surface area. There might even be a surface volume. If you're in four dimensions, which is really weird to think about. So that's what we're doing here. We're trying to find a signed hypervolume, right? So it would be positive if it lies above the XYZ plane or hyperplane, let's call it. Negative if it lies below the XYZ hyperplane. I guess we'll just call that space. XYZ space. Now, what the hell does above and below mean in the fourth dimension? Beats me, but that's what it is. So that's essentially what we're finding here, a signed hypervolume. Again, triple integrals are going to be set up as iterated. We're going to go integral 0 to 2, integral 2 minus y to 6 minus 2y, integral 0 to root 4 minus y squared of z, and then the order of integration that we chose, dz, dx, dy. Fubini's theorem still applies, meaning the order doesn't matter. Right? You can choose any order you want. The description of your domain is going to change. But you'll get the same answer as long as it's set up the right way. Yeah. Right, antiderivative z is a half z squared. Evaluate that from 0 to root 4 minus y squared. You're going to be left with a half 4 minus y squared. Before times the length of that interval. 6 minus 2 is 4. Negative 2y minus negative y minus y. Yep. And then it's going to be minus 1/3. Oh, wait, what am I doing? This is with respect to x. That 4 minus y squared is a constant. So it's 4 minus y squared times that length, which we just said was 4 minus y. Six minus 2y minus 2 minus y. All right, 6 minus 2 is 4. Negative 2y minus negative y.
Why could you do that? Because it was a constant the whole.
With respect to x, 4 minus y squared is a constant, yes. So just group it together.
No, but why could you subtract 6 minus 2y?
Because there's no x, right? It's the length of that interval. So upper minus lower. (16 minus 4y minus 4y squared plus y cubed. (16 times 2 is 32. That'll be 2y squared, so that's 2 times 4. 4/3 y cubed will be 4/3 8. 32/3. And then plus y to the 4th over 4. 16 over 4 is 4. Love it when my intervals start at 0. Be what, 28 minus 32 over 3. Common denominator is going to be 3. 28 times 3 is 84. And then 84 minus 32 would be 52. Be 52 over 6 is 26 over 3. That would be the signed hypervolume. And for our purposes, just the integral. I re-knocked. What's going on? What's going on? Yes. What is going on? Because of this. Snooze option isn't showing up. You give me more luck. What is going on? Why are you not syncing? Oh, why did it go there? That was odd. Find the volume bounded by the paraboloid z equals 2x squared plus y squared and the cylinder z equals 4 minus y squared. What do I want to do? Minus 5 to 5, let's say. Okay, let's try and get an idea. I set it that way. Right. So what we're trying to find, this is actually a really good look right here. Is the volume of that. Right, it's inside the paraboloid, but below the cylinder. do this just so I can actually see the cylinder. Do that just yet. This is what we're looking for. We can go ahead and try and describe W right off the bat. If we really wanted to. Would be the easiest way to do that. X goes forward to backwards. So Y would go. Oh, that's fun. Yeah. All right, Z would go from 2x squared plus y squared to 4 minus y squared. X would go zero. No. Be negative. Dear. That wouldn't work. Yeah, go from here to here. Which doesn't make any sense. Oh, each other. Okay. Back. Right, so x would go negative square root of 2 minus y squared. To that positive square root. That should be a minus y squared, not plus. And then y would go negative root 2, positive root 2. Right? Or you could try and do it. So this was what? Dx dy. You could also try and do it dy dx. Ooh, that's hideous. Right. So if you wanted to do it that way, this would be the setup. Have 4 minus 2x squared minus 2y squared dx dy. Could factor out a 2 to make this easier. That does not look fun. There is another way of representing triple integrals. And that's as an iterated integral, a double integral iterated with a single integral. And then your differential volume would just be pull out whichever one you're integrating with respect to, in this case, z, and then it's times differential for a, right? Because that's what volume is. Volume is a height times area of a cross section. So what we do is set it up as that type of iterated integral. Now we have double integral over some two-dimensional domain of 4 minus 2x squared minus 2y squared dA. Let's take a look at that domain. The two-dimensional domain is going to be the curve of intersection, isn't it? Curve of intersection is just where the z's are equal. Let's go ahead and just label it. Curve of intersection is a circle. Specifically, a circle of radius √2. So why not just do that double integral in polar coordinates? How would you describe this region as a polar region? It's a circle of radius √2.
The radius here, the.
Now, what about theta? And this is where we'll pick up on Thursday.